Welcome to this advanced manufacturing and process modeling course. So, now we have reached to this metal forming module of this course. So, we have already discussed about casting, we have discussed about welding and also powder metallurgy. So, the primary processing techniques, primary processing techniques of manufacturing, that is mostly casting and powder metallurgy. So, along with that it is the metal forming also we use to get the desired geometry of the part and with the desired properties. However, metal forming largely differentiates with metal casting and powder metallurgy based techniques in terms of the microstructure, that is a preferential flow of grains that we can observe in case of formed parts, and also the mechanical property. So, the formed parts, the parts or components developed by the metal forming route outclass the cast and powder metallurgy process parts by mechanical property, by a large margin in most of the occasions, unless barring some special cases. So, it is very important part of the advanced manufacturing process that we will be discussing in this module. So, we will start, so we will be discussing about introduction to metal forming, forging, rolling, extrusion, wire and tube drawing, hot cold working, and different analysis techniques of metal forming processes such as slab analysis of rolling process, slip line analysis of punching, etc. So, so what is metal forming basically? So, it is a large set of manufacturing processes in which the material is deformed plastically to take the shape of the die geometries. The tools used for such deformation are called die, punch, etc., depending on the type of process. So, the importance of metals in modern technology is due in large part to the ease with which they may be formed into useful shapes such as tubes, rods and sheets. So, the useful shapes may be generated in two basic ways: by plastic deformation processes, in which the volume and mass of the metal are conserved and the metal is displaced from one location to another location, so that it can assume the shape of the desired part geometry. So, that is the goal in case of metal forming that we follow, and in case of there is other techniques of metal forming is by metal removal or machining process. We will discuss it within the scope of this course later, in which material is removed in order to give it the required shape. So, the processes may be classified into only a few categories on the basis of the type of forces applied to the workpiece as it is formed into shape. So, we are talking about classification of metal forming processes. So, they can be categorized as direct compression type processes, indirect compression type processes, tension type, bending type processes, and shearing processes. So, these are the 5 broad classifications of the based on the load applied for forming the metal object. We can classify metal forming into these 5 type of processes. So, plastic working processes which are designed to reduce an ingot or billet to a standard mill product of simple shape such as sheet, plate and bar are called primary mechanical working processes, and forming methods which produce a part to a final finished shape are called secondary mechanical working processes. Most sheet metal forming operations, wire drawing and tube drawing, are secondary metal working processes. So, that terminology in this area is not very precise. However, frequently the first category is referred to as processing operations and the second category is referred as fabrication. So, that is why we call at sheet metal fabrication. So, for example, so this bending, this shearing, and die stretch forming, these comes under fabrication, whereas the processing metal forming, the examples are like forging and then rolling. So, this is a typical 2 high rolling example that is shown over here, and then this is a typical example of extrusion. So, it is more precisely can be said as forward extrusion. So, where you can see the extruded billet is going moving in the same direction, in the direction of the applied load. So, hence So, this is a case of forward extrusion, and again deep drawing, so and also wire drawing. So, these are examples of processing, primary forming processes, and these are called the fabrication techniques, which are mostly applied for the sheet metals. Okay. So, so you can see here the load applied is mostly compressive in nature. So, that means these are compressive load. So, all these cases the direct compression, that is why they are called as direct compression type processes, and there are some processes where the direct compression is not applied. For example, you see this is a particular case. So, here this is a indirect compression type process. Okay. So, this is a direct compression type process. So, this is how you need to understand based on the loading condition applied, we can classify the primary forming processes into direct compression, indirect compression, and even tension processes. Okay. Yeah. This is a typical example of a bending process, and also so shearing processes are this much, and this is also an example of bending process. So, these are basically the shearing process. Okay. Yeah. So, the deformation processing situation is viewed as a total system. The deformation zone is concerned with the distribution of stress, strain, and particle velocities. So, this is a typical deformation zone. So, this is the undeformed metal which is pressed within this extrusion dies, and this is the extruded product. Again, this is a typical example of a forward extrusion, where the direction of the movement of the extruded bullet and the direction of the applied force is same. So, that is why we call it as forward extrusion process. So, the deformation zone here, so this is the typical deformation zone. So, is concerned with the distribution of stress, strain, and particle velocities, and with the overall pressure required to perform the operation. Obviously, the applied forces must develop yielding in the material, but the stresses must not create local fracture, crack propagations, which can damage the surface and also subsurface features of the workpiece that is undergoing deformation processing, and in general it can lead to catastrophic failure or the generation of subsurface or subsurface cracks, which can cause catastrophic failure when the deformed object is subjected to the in service conditions or in service loading conditions. Okay. So, the applied forces here, the applied forces must develop yielding in the material. So, the such metallurgical phenomena as strain hardening, recrystallization, and fracture are important in this case, in deformation processing. So, but often under specialized conditions of high strain rates and or high temperature. So, these are the typical conditions that are applied in case of metal forming. So, the flow stress of the material will be a strong function of strain, strain rate, and temperature, often at values of these variables that are difficult to simulate in the laboratory. So, the workpiece will be in contact with non-deforming elastic tools or dies, and the friction along this interface and the heat transfer from the workpiece to the die are important considerations, as are such practical concerns as tool wear and surface finish of the product. Okay. So, the forming can be largely classified as bulk forming, then sheet forming, and then powder metal forming. So, the powder metal forming can be classified as powder forging, powder extrusion, powder injection molding. Okay. And sheet metal forming is like deep drawing, blanking, punching, piercing, bending, and shearing. And bulk forming, as we have discussed, it can be subdivided as primary operation and secondary operation based on to achieve the wrought object, arriving at the wrought billet or wrought ingot from the cast ingot. So, this is the in the form of shapes such as bar, sheets, plates, tubes, and then these are bar, sheets, plates, tubes, then undergo the secondary operation, that means which are called forging, extrusion, drawing, straightening, and sizing, to arrive at the desired either the desired part geometry or the desired level of mechanical and metallurgical and microstructural attributes needed in the final part. And then from this secondary operation processed billets, forged or extruded or drawn billets, those parts can be machined. So, this is the this is the classification of metal forming processes. So, the primary reason for plastic deformation, that happens during metal forming processes happens due to the motion of dislocations. So, then it is very important to understand the dislocations. So, dislocations can be classified as two basic types like edge dislocation and screw dislocation. So, the theoretical strength of a perfect crystal were much higher than those actually measured. So, it was determined that this discrepancy in mechanical strength could be explained by dislocations. So, on a macroscopic scale, plastic deformation corresponds to the net movement of large number of atoms in response to an applied stress. So, it is the direction of motion. So, edge dislocation line moves parallel to the applied stress. So, this is a typical example of edge dislocation. So, it signifies that there is a slip happens on along a slip plane, that is basically it can be understood as a displacement of one plane of atoms over with respect to the another plane of atoms along a plane, along which plane is called slip plane. So, in an edge dislocation, localized lattice distortion exists along the end of an extra half plane of atoms. So, we will learn it even detail in the next slides. And then a screw dislocation results from shear distortion. So, you can see where you can see the it is the direction of motion which is you can see it is in case of edge dislocation the movement is parallel to the direction of motion, whereas in case of screw dislocation it is in the perpendicular direction to the direction of motion. So, this is a clear clear point to distinguish between edge dislocation and screw dislocation. Okay. So, many dislocations in crystalline materials have both edge and screw components, and they are called basically the mixed dislocations. So, screw dislocations moves perpendicular to applied stress, edge dislocation moves parallel to the applied stress. Yeah, so it can be understood. So, the edge dislocation can be understood better from this schematic, which shows the the array of atoms from where there is a half plane of atoms which is marked here at location A, which is which is a dislocation, and then there is a slip plane. So, this is the edge dislocation line. So, it is basically moves along the right hand side by breaking the bond between these array of column of atoms, you can say. So, then from it you can see that this half plane of atoms shifts its location towards right from location A to location B, and likewise it shifts towards the end of the the full architecture of the atoms, and then it is now reaching at the last last plane, that is this is this is how the edge dislocation moves from the inner plane to the outermost plane, and then it appears to be a slip. It appears to be like a slip if you compare it with the previous schematic. So, this is how you can understand it. So, you can see that there is so this is basically the extra slip of the this half plane of atoms, and along this along the slip plane. So, here it serves as the slip plane, along which plane this the extra half plane of atoms move from one edge to another edge. So, this is a typical example of a edge dislocation that we have discussed in the previous slide as well. Okay. So, the extra half plane of atoms A is forced to the right, thus pushes the top halves of planes B, C, D in the same direction. By discrete steps, the extra half plane moves from left to right by successive breaking of bonds and shifting of upper half planes. That is what is depicted in this schematic. A step forms on the surface of the crystal as the extra half plane exits. So, this is basically the step that is mentioned over here. Okay. So, the plastic deformation, if the solid body is loaded beyond the elastic limit, the body will experience a permanent change. So, this is generally happens beyond the yield limit. I mean yield stress of that particular material. So basically the measure of plastic deformation can be defined as the the deformation which cannot be retrieved. I mean the material which undergoes plastic deformation, it cannot come back to its original shape when the load is removed from the so when it is unloading, even after unloading, the material assumes a permanent deformation, and that is why it can be stated that it has deformed plastically. It means plastic flow of matter happened. I mean that the applied loading condition generated stresses which is beyond yield stress for that particular material. Okay. So, so the body will experience a permanent change in shape and size even if the load is removed. So, the plastic deformation of metals and alloys is generally studied under two categories, namely plastic deformation of single crystals and plastic deformation of polycrystals. Okay. So, the plastic deformation of single crystals. So, the plastic deformation of single crystals involves the study of one single crystal and observing how it behaves under stress. So, a typical single crystal is nothing but a single grain and has no grain boundaries. So, the plastic deformation in single crystals may take place by slip, may take place either by slip or twinning or a combination of both slip and twinning. Okay. So, it involves sliding of blocks of crystals over other slip planes. So, and slip occurs when shear stress applied exceeds a critical value. So, slip occurs most readily in specific directions, that is slip direction. So, there are two things, one is slip plane, another is slip direction, and so the specific directions on certain crystallographic planes. So, feasible combination of a slip plane together with a slip direction is considered as a slip system, which is very important to understand the deformation, plastic deformation behavior of a particular material under a particular set of loading condition. So, during slip, each atom usually moves same integral number of atomic distances along the slip plane. Okay. So, so this is a example is drawn to this figure, that is figure A. So, a shear stress is applied to a metal cube with a top polished surface. So, the slip occurs when the shear exceeds the critical value. So, the atoms move an integral number of atomic distances along the slip plane, and a step is produced on the polished surface. And when, so that is basically a typical example of a slip. More you can also term it as a edge dislocation. So when we view the polished surface from above with a microscope, the step shows up as line which we call as a slip line. If the surface is then repolished after slip has occurred, then the slip plane, that slip line will be gone and the step is removed. So, the slip line will disappear. So, so this is the classical idea of slip that is shown over here. So, you can see that this is because of the shear stress applied, there is a shifting happened, in the direction of the applied stress. Hence, it is it is a typical example of edge dislocation, and where you can see the slip happened and along the slip plane. So, which is, so this is typically the slip plane, and this is the slip direction, and then when it is repolished, then this step is gone, and that is what is shown here. So, so this is a case of a slip. So here another schematic, that is the movement of the edge dislocation, that is also discussed earlier, and how it is basically moving from left to right by breaking the atomic bonds and exiting by the rightmost side of the atomistic system that has been considered here. So, this is the atom movements near dislocation in slip, and B is the movement of an edge dislocation. So, this is exactly what we have discussed earlier, that is, and then this A shows the atomic movements near dislocation in slip. So, what are the differences? So, in figure A, the extra plane of atoms at the edge dislocation initially is at 4, and then under the action of shear stress, a very small movement of atoms to the right will allow this half plane to line up with the half plane 5, at the same time cutting the half plane 5 from its neighbors below the slip plane. So, by this process, the edge dislocation line has moved from its initial position between 4 and 5 from to a new position 5 and 6. So, this is how a edge dislocation moves, which is explained with this schematic just beside this. So, since the atoms around the dislocations are symmetrically placed on opposite sides of the extra half plane, so the equal and opposite forces oppose and assist the motion. Thus, in a first approximation, there is no net force on the dislocation and the stress required to move the dislocation is 0. The continuation of this process under the stresses shown in figure moves the dislocation to the right when the extra half plane of atoms reaches a free surface. So, it results in a slip step of one Burger's vector or one atomic distance for the simple cubic lattice. Okay. So, so the extent of slip depends on many factors, external load and the corresponding value of shear stress produced by it. So, the crystal structure, orientation of active slip planes with the direction of shearing stresses generated. So, the slip occurs when the shear stress applied exceeds a critical value. And so, for single crystal scheme out define critical shear stress as tau r. So, which is equivalent to P cos alpha divided by A by cos xi. So, then it becomes equal to P by A into cos lambda cos xi is equal to sigma, that is the normal stress. P by A is equal to sigma and cos delta into cos xi. So, in a polycrystalline aggregate, individual grains provide a mutual geometrical constraint on one another, and this precludes plastic deformation at low applied stresses. So, you can see this is a typical slip plane, this is the slip direction. So, here this is the normal load acting over this single crystal, and then this is a n normal over the slip plane, and then this is the direction, that is the slip direction. So, this is slip direction and the normal to the plane. So, the normal to the slip plane is also normal to the slip direction. So, this is how the system, and the included angle between the normal to the slip plane and the axis of the normal load applied over the single crystal is phi, and the angle between the slip direction and the load axis of the load applied at the center line is delta. So, this is how it is described here. And then, so the slip in polycrystalline material involves generation, movement and rearrangement of dislocation. So, during deformation, mechanical integrity and coherency are maintained along the grain boundaries. So, a minimum of 5 independent slip systems must be operative for a polycrystalline solid to exhibit ductility and maintain grain boundary integrity. So, as given by von Mises. So, there must be a 5 independent slip systems for a polycrystalline solid. So, these are some examples of typical crystal structure, that is face centered cubic, body centered cubic, hexagonal close packed, etc., and their individual slip planes and slip directions. So, like for FCC it is 111 and slip direction is 110, and for body centered cubic the more common slip plane is 110 and less common slip planes are 112 and 123. Whereas slip direction is common for both all the kind of slip planes, which is 111, whereas it is little different in case of hexagonal close packed, whereas in this case more common slip planes are basal plane and least common are prismatic and pyramidal planes, and slip directions are close packed directions. Okay. So, the plastic deform mechanisms, that is twinning. So, it results when a portion of a crystal takes up an orientation that is related to the orientation of the rest of the untwinned lattice in a definite symmetrical way. So, the important role of twinning in plastic deformation is that it causes changes in plane orientation, so that further slip can occur. Okay. So basically the role of twinning is to promote plastic deformation. Because it is allowing the change in plane orientation. So, further slip, that means further glide of dislocations. So, that means this is how it is facilitating plastic deformation. Twinning also occurs in a definite direction on a specific plane for each crystal structure. So, like we have learnt earlier that there is a specific shear plane, slip plane and slip direction. Similar to that, twin planes are also fixed for particular crystal structure with a definite twinning direction as well. So, for FCC example are silver, gold and copper. The typical twin plane is 111 and twin direction is 112, whereas in BCC it is 112 as the twin plane and 111 as the twin direction, and in case of HCP it is 101 bar 2 as twin plane and twin direction is 1 bar 0 1 1. So, so this is a typical example of twinning. I mean, so this is the twin plane, and as we have discussed above, so the other part of the crystal takes up an orientation that is related to the orientation of the untwinned lattice. So this is symmetrical. So you can see this part along the center line along the twin plane, and this part is symmetrical. So that is what these are, I mean, this is a typical example of twinning. And then this is the another example of twinning. So you can see that there is symmetry between the crystal, I mean lattices in the both sides of the twin plane. So that is why, I mean, we can say that the twin is existing in this case, and the particular plane for individual crystal structure and the twin direction are depicted in this table. Okay. So, move ahead, we will go ahead into the mechanism of metal working or the mechanics of metal working. So, assumptions, so during plastic deformation the volume of metal is conserved. So, assume this typical case. So, I mean, so this is here you can see this is the height. So, this is a cylindrical object having area. Okay. So, then what will be the, I mean, typical volume? So, that A0 into H0. So, and here it is the, so I mean, because we are basically reducing the height from H0 to HF, that means we are basically applied compressive load. So, the cross sectional area is bound to increase because volume has to be, I mean, conserved. So, that is how, I mean, this is how the, I mean, metal working processes works. So, in case of conventional strain, it is the final height minus the initial height divided by the initial height. So, HF by H0 minus 1, and true strain, it is the integration dH by H from H0 to HF, that is ln, I mean, HF by H0. So, because HF is lesser and H0 is higher, we are talking about compression. So, hence the true strain is basically negative. So, that means minus ln, I mean, so we can express it as is, I mean, because it is a lesser value and the higher value, we can also express it as minus ln H0 by HF, and the calculated strains will be negative, indicating compressive strains. So, then, I mean, so this is, so in metal working problems it is common practice to reverse the convention, so that compressive stresses and strains are defined as positive. So, we are only concerned about the magnitude here, and that is why we are using the subscript C for, I mean, both conventional strain, that is E as termed as EC, so that it can be expressed as positive, and epsilon true strain has been termed as epsilon C, again for the similar reason. So, hence epsilon C can be expressed as ln H0 by HF. So, so because of, so this subscript C takes care of the negative sign that comes because of the compressive nature of the, I mean, deformation. So, in metal working deformations frequently we are expressing the reduction in cross sectional area, the fractional reduction in this case as defined as R is equal to A0 minus AF by A0. So, from the constancy of volume relationship we know that AF HF is equal to A0 H0. So, I mean, so then so R is equal to, we know that 1 minus, so it is equal to 1 minus AF by A0. Hence, we can see that, I mean, epsilon is equal to ln HF by H0. So, yeah, so it is coming from this expression. Okay. So, then ln HF by H0, so then is equal to ln. So, from here we know that HF by H0 is equal to A0 by AF. So, that is what is kept over here, and again from here from the expression of R we know. So, AF by A0 is equal to 1 by R, oh sorry, 1 minus R. So, then putting that value over here, so we know that AF by A0 is equal to 1 minus R, that means A0 by AF is equal to nothing but 1 by 1 minus R. So, that is the value is placed over here. So, ln 1 by 1 minus r. So, that is the epsilon, that is the true strain. Okay. So, the requirement of a theory. So, describing the mechanics of a metalworking process is the ability to make an accurate prediction of the stresses, strains and velocities at every point in the deformed region of the workpiece. So, the various approaches differ in complexity and in the degrees to which they meet this requirement. In general, such a theory consists of three sets of equations, which are the static equilibrium of force equations, the Levy-Mises equations expressing a relationship between stress and the strain rate, the yield criterion. So, the methods of analysis in increasing order of complexity and ability to predict fine details are the slab method, which assumes homogeneous deformation, and another is uniform deformation energy method, which calculates average forming stress from the work of plastic deformation. So, out of these there are some other techniques also, which are not discussed here for keeping it focused based on the time constraint. So, because this course includes several manufacturing aspects and also process modeling aspects. So, to discuss all these techniques of this prediction of stress, strain and velocity. So, like one another technique that I would like to emphasize here, which is also relevant to this course, that is finite element modeling. So, by numerical methods also we can predict the stresses, strains and velocities at every point in the deformed region. But for now, for analytical calculation, we will focus more on the slab method, and we will learn how we can predict, evaluate or analytically calculate the stress, strain and velocity distribution at every point in the deformed region. So, but we will start that in the next class. So, for this class we are stopping here, and so we will meet in the next class. Thank you.